So why 1 over beta learning rate working so well? Let f be a beta smooth function, then we have this inequality, gradient of fx minus gradient of fy norm, which is always less than or equal to beta times the distance between x and y. So assume that there exists a unique global optima, then at the optimal point x star we have gradient of fx star equal to 0. So we can say this, gradient fx norm, which always less than or equal to beta times the distance between your current point x and the optimal point x star. So when you set gamma equal to 1 over beta, the distance between your current point xt and your next update point xt plus 1, which is equal to gamma times gradient of fxt norm from the definition of gradient descent. And this one, which is always less than or equal to the distance between the current xt and the optimal point x star. Okay, so which means every time if you have this xt point and if there is x star point, the optimal point, your update essentially always bounded by this area. So you cannot cross, you cannot pass by x star, you cannot go more than x star. So which prevent the oscillations or diverge. Basically, when gradient descent fails, in that case, your running rate is too huge, so your update pass through the optimal point x star and go to some very far away area. But with 1 over beta learning rate, we can at least guarantee that your each update is restricted and we can prevent any oscillation or divergence. So this is one very nice property. And also from the previous slide, we can also guarantee very nice convergence rate 1 over capital T. With strong convexity, essentially 1 over beta learning rate can guarantee more. We can guarantee linear convergence rate. The linear convergence rate, the definition is this: a sequence of f0, fx1, and so on is said to converge linearly to fx star as t equals to infinity if there exists some constancy between 0 and 1 such that fxt plus 1 minus fx star over fxt minus fx star is equal to c. So which means every time we can decrease the objective function value with some constant amount. So with this, we can say fxt minus fx star is less than or equal to g to the power t fx0 minus fx star. So exponentially, we can exponentially decrease the objective function value. So we can expect very fast convergence to your optimal point x star. Okay, so this is most desirable property for optimization problems. So from the vanilla analysis again, we have this gradient of fxt transpose xt minus x star is equal to gamma over 2 gradient of fxt norm square plus 1 over 2 gamma times xt minus x star norm square minus xt plus 1 minus x star norm square, which comes from the vanilla analysis. And from the alpha strongly convexity, we have this. This is just definition of alpha strongly convex. So when we combine this one and this one together, we have this. Okay, so because we have a common term here and here, we just rewrite A and B like this way. Okay, we can combine A and B in this way. And so from the above, we have this inequality, xt plus 1 minus x star lambda square minus 1 minus alpha gamma times xt minus x star lambda square is less than or equal to 2 gamma fx star minus fxt plus gamma square gradient of fxt lambda square. Okay, so yeah, it's okay. So that this page, I just used the definition of alpha strongly convexity and very simple analysis from vanilla analysis slide, and I just combined the two things A and B. Okay, so in the smooth convex function case, we know that the optimal step size for beta smooth function is 1 over beta. So let's put gamma equal to 1 over beta. Okay, then we have this property, 2 gamma fx star minus fxt plus gamma square gradient of fxt square, which comes from the here, this part. Okay, so I want to upper bound this term. So this is equal to 2 over beta fx star minus fxt plus 1 over beta square gradient of fxt square when we set gamma equal to 1 over beta. And since fx star is the optimal point, fxt plus 1 always greater than or equal to fx star. And from the beta smooth property, we know this one, fxt plus 1 minus fxt, which is less than or equal to minus 1 over 2 beta gradient of fxt square, which is in page 10 of this lecture slide. Okay, so let's go to page 10 here. Okay, so we have minus 1 over beta square gradient of fxt norm square plus 1 over beta square gradient of fxt norm square. So essentially we have this term is always less than or equal to 0. Okay, so indeed when gradient of fx star is equal to 0, we have this property, fx minus fx star is always less than or equal to 1 over 2 alpha times gradient of fx square, and this is greater than 1 over 2 beta gradient of fx norm square. Sorry. Anyway, therefore, from the previous page, we have this xt plus 1 minus x star norm square is always less than or equal to 1 minus alpha over beta times xt minus x star norm square. So every time we decrease the distance between your current point and the optimal point x star, n is 1 minus alpha over beta factor. Okay, so when alpha and beta is close together, so which is close to 1, basically with very few steps we can go to very close to x star. And with capital T number of iteration, we can say xt minus x star square is less than or equal to 1 minus alpha over beta power capital T x0 minus x star square. So basically exponentially decrease the distance between your current point and the optimal point x star, which is very nice. This is linear convergence rate. So from the beta smoothness, we can go one step further. So we can write down the convergence rate with respect to the objective function value fxt minus fx star, not the just point distance between x capital T minus x star num square. So from the beta smooth property, fx capital T minus fx star is less than or equal to the gradient of fx star transpose xt minus x star plus beta over 2 xt minus x star square. And we know that this one is equal to 0, so we can ignore the first term. And we also know that this term is exponentially decreasing starting from x0 minus x star, and this one is exponentially decreasing. So in the end, we have this one. So in the end, we can guarantee some linear convergence with term 1 minus alpha over beta. So this is C in the linear convergence definition. Okay, so this is very nice. And so when your objective function is alpha smooth, alpha strongly convex and beta smooth, and alpha and beta are close together, we can expect very fast convergence with simple gradient descent approach. Okay, and alpha over beta, which is called condition number. So this value in between 0 and 1. So when alpha beta is matched, so this is equal to 1, we can immediately go to the optimal point. And quadratic function has this condition value equal to 1. But when this value close to 0, then although we can say some linear convergence rate, the C term is very close to 1, so which means we need still a lot of iterations to converge to optimal point.